Hello, my name is Rob Reynolds. Welcome to section 2.2 of Business Calculus. Today we're going to continue talking about how to find the derivative, and the topic is differentiation. The objectives of this is to look at the constant rule, the power rule, and then the constant multiple rule. We will definitely get to eventually the chain rule, but probably not in this lesson. That's for composite functions. The most important thing right now is this power rule, so we don't have to use the limit process, which we learned on the section 2.1. This is cumbersome, and we don't want to have to take the limit process to find the derivative. There's a faster way, and the first definition that we're going to get is the derivative of a constant is always zero, and here's the proof of why. So again, the derivative of a constant is zero. You could work through that if you'd like. So here's a couple examples. Please go to Blackboard and download the worksheet so you can follow along in this video. But the derivative of 7, you should know, is 0. The derivative of 0 is 0. The derivative of 2 is 0. And the derivative of -3/2, you guessed it, 0. The next thing we're going to look at is the power rule. So we don't have to use the limit process. If I give you a function like y is equal to 5x cubed, we're going to use the power rule, which says multiply that 3 times the 5 to get 15, and then decrease that exponent by 1 to a 2. So this actually you've seen before in part of the binomial expansion. There's my y squared double square rule that I talked about in the other video, but you can see there's, if I put it in general form, there's the general rule. So you multiply n times this 1 if there's nothing out there, and then decrease the exponent by 1. So here comes a definition. The derivative of x is 1, because x to the first 1 times this 1 is just 1. And if I decrease the exponent by 1, I get a 0. And of course, you know x to the 0 is 1. And 1 times 1 certainly is 1. So the derivative of a constant is 0. The derivative of x is 1. Well, and then you could look at the graph of this and just say, yeah, the slope, the derivative is the slope. It's rise over run. So when I mention derivative, that means the slope of the tangent line. So before you find the derivative of something that looks like 1 over x squared, you may want to rewrite that to be y is equal to x to the -2nd. So it's in this form that makes it easy to find the derivative. So you can see in this example, -2 times this 1 is this -2, and then they decrease that -2 to -3. Remember, this is the slope of the tangent line. That's what derivatives find. Well, this is the slope formula for any x value. So that once you find this slope formula, you could find uh, uh, the slope at any given point. So if I let x be 2, I could find the slope at x equals 2 by plugging it into that formula. So again, finding the derivative in the fast way without using the limit process, you'll have to demonstrate that you can use the limit process in section 2.1. But if I don't ask you to use the limit process, just say that find the derivative, you can use the power rule. So again, the power rule says multiply the exponent 3 times 1 and get a 3, and then decrease the exponent by 1, so 3 goes to 2. Sometimes when you do a quick little rewrite, and you rewrite this as an exponent, so it's -2 times the 1 is -2. Don't leave negative exponents in the answer. If you could clean that up and put the exponent back in the denominator, I'd appreciate it. So I think my math lab will accept answer A or B, but just to make sure, this is the more simplified form without any exponents. And again, the derivative of x is 1, and the derivative of t is also just 1. So go ahead and do a quick rewrite for that second example. If I were to ask you to find the slope at these given points, then go ahead and find the derivative first, which is 2 times this 1, which is 2, x to the first, and then go ahead and just evaluate by plugging in a -2. So 2 times -2 is -4. Plug in a -1 to the slope formula. 2 times -1 is -2, and complete this process. F of 0 is 0, f of 1 is 2, and f of 2 is going to be 4. Again, you can go to Blackboard and see the worked out solutions. They're all posted there for you in a nice PDF file. So example 3, again, just kind of show you what's happening here is I'm finding slope at several different points. There's the slope at 0, the slope at 2. You can see it's getting steeper, and down here the slope is negative at f prime negative 2. The slope should be negative because the function is a y equals x squared. The constant multiple rule says that if you see a constant, you can pop it out front. It doesn't seem like a very helpful rule at first, but it becomes helpful later when things get a little more complicated. Again, if you have a constant here, you can just pop that constant out. Let me demonstrate that for you, and then you're going to think it's ridiculous to try to do that rule. But if I give you y is equal to this, you actually could go find y prime by popping the 5 out and just taking the derivative of the x cubed, which is, this is bad notation, but you'll understand what I'm doing here, 5 times, which is 15x squared. You're going to say, no, I never want to pop that constant out because this 3 times the 5 and decrease the exponent by 1 is much simpler because it's less work. But later, when the problems get more complicated, popping that constant out becomes like a powerful tool just to kind of clean things up. I wouldn't do it in this example that I gave to you because it was more work, but it does become a powerful tool later on when things get more complicated. Notice that the derivative, if I give you 5x, the derivative of that would just be 5, and that's what this is talking about. It's just a constant. Well, that's because this 1 goes to an x to the 0, which you know is just 1. So again, a couple other examples. Be really careful with these parentheses. These all mean different things. This is really 5 halves times x to the negative third, where the 2 stays in the denominator, but this 2 is actually being cubed, so this is really 5 over 8x cubed, which, to take the derivative of that, would be this. This would be 7 over 3x squared before I took the derivative. Again, these are all just the functions. And this would actually be 7 times the 3x whole quantity squared, which is 7 times 9x squared, which I would simplify first to be 63x squared before I found the derivative. So again, do a quick little rewrite and be really careful with these parentheses, what those all mean. For example 4, I hope you've gone to Blackboard and you printed out example 4. You can work this before I work it, hopefully. You're going to take 1 half times the 2 and then decrease the exponent by 1. So this is going to be 1, which I won't write, x to the negative 1 half, which, again, a quick little rewrite would be 1 over the square of x. For part B, I would probably write this as 4/5 t squared. So we want to do 4/5 times the 2 and decrease the exponent by 1. You don't need to show that work. If you can skip this step, that would be great. And just get 8/5 t. Again, worked out solutions are on Blackboard if you'd like to go to the PDF file. Example number 5 says, if I do a quick little rewrite, I could do 1 times this guy and then decrease it to x to the 0, which is just negative 3 halves. The second part, example 5b, treat 3 pi as the constant, and then it's to the first. So 1 times 3 pi is just 3 pi, x to the 0, which is just 3 pi. And then this, I would do a quick little rewrite, and then 1 times the negative 1 half is negative 1 half, x to the 0 is just negative 1 half. Again, here are solutions. Check out the PDF file on Blackboard. Try these. See if you can do a quick little rewrite. Pause the video, and remember, it's best if you go ahead and try to work through these instead of just watching me work through problems. You learn best through, well, really making some errors and asking the question, why can't I work the problem the way that I tried to work it? That's more valuable than just saying, hey, here's how to do it. So again, a quick little rewrite, then differentiate, and then simplify it. Those are the steps that you want to follow. So before I reveal all of these, go ahead and see if you can find these derivatives. Pause the video, and again, do a quick little rewrite, then do the derivative, and then do the final step of rewrite. Pause the video. see if you're correct. If you're not, you can take a snipping tool and screenshot of this and email this to me. And ask me why you can't do it the way that you did it, or why is it the answer something different. And then same with this 126x. And I'm going to skip this because we just talked about it on the last slide, but walking through it. So remember, when working with radicals, you can always change those or rewrite those to exponents, and that makes it a heck of a lot easier to find the derivative. So if I have y is equal to the square root of x, you should recognize this as a little 1 and a 2 here, even though I don't write it. And you can write that as x to the 1 half. Makes it pretty simple. So this is 1 over x to the 4 thirds. The root here is 3. It's pronounced the cube root of 4, and roots on a tree grow on the bottom. And then you could write that as x to the negative 4 thirds. So a quick little rewrite when you see radicals will really help you find the derivative. This again, we already talked about x to the 1 half. Differentiate that, and then simplify. Again, I would encourage you to pause the video, see if you can do a quick little rewrite. Pause the video, see if you can find the derivative of this before I reveal it, and simplify this. That's the procedure that you should be thinking about. Again, pause the video, go to Blackboard, print out this problem. You can actually write on a worksheet that I posted on Blackboard, so you can work through these problems. The worksheets are not due. You do not need to submit them, but boy, you'll learn a lot if you go through this process. So the sum and different rules are pretty simple. It just says if you take the derivative, you have a function, and you want to find the derivative of maybe 3x squared plus 5x, you could literally just take the derivative of the first guy, 3x squared, and then find the derivative of the second guy, the 5x, and just add them together. So it's as simple as that. So the derivative of 3x is 3, and the derivative of 2x cubed is 6x squared. Derivatives work just like limits, pretty simple. So you can just distribute literally this derivative of the f of x and g of x, and that works for addition and subtraction. Be careful, I'm just going to say right now, this does not, even though it works for limits, it does not work for addition. So if you have the derivative of, maybe you don't know the derivative of sine yet, but we'll get to that. Sine times 5x, you cannot just take the derivative of sine and then the derivative of 5x. Tell me the answer. So this does not work for multiplication, although limits does. For addition and subtraction, you just take the derivative of each individual. So the derivative of x cubed is 3x squared plus 8x. The derivative of this is 6x, and the derivative of this is negative 2. Solution. Remember, when they use the word slope, they're asking for the derivative, or the slope of the tangent line. So the derivative of this is 3x squared minus 4x, and the derivative of this is just 0. And then you want to find it at this point at x equals 1. So I'll find f prime 1. 3 times 1 squared minus 1 is 3 minus 4, or negative 1. So negative 1 is the slope at that point. You could do a quick little graph, and then certainly see that the slope is negative 1 at this point, 1 comma negative 1. So the y value is not even important. You could do the same thing with example number 10. Find the derivative of this and simply evaluate g prime at negative 1 to get a 9. The practical application of this, there it is, 9. So then, by the way, with that, with the slope at this point, they didn't ask in this problem, but we could go ahead and then write the equation of that tangent line, which is this guy, y equals mx plus b. You know how to write the equation given slope at a point. They didn't ask in this problem. Maybe they did. There it is. So I would go to y equals mx plus b, where we found the slope was 9, and the point that we were using was this guy, negative 1, negative 3 halves. So I do it a little bit differently. The book goes to this y minus y is equal to the slope of x minus x. If I was finding the equation of the line, I would plug in this y value. This y is this y. So I would write down negative 3 halves is equal to the slope. The x value is negative 1 plus b. And I would simply solve for b, which evidently should turn out to be 15 halves. Let's see. We can do a little mathematics. By adding 9, which is the same thing as adding 18 halves, and come up with a b value. So negative 3 halves and 18 halves, sure enough, 15 halves, and I get the same equation. So you're certainly welcome to do it. Call it method A, the book method, or I usually like y equals mx plus b. I'm just familiar with that. The application here is that you need to know is the derivative is the slope of the line, slope of the tangent line. Oftentimes in business calc, they'll call that the rate of change. Rate of change is simply the slope, how fast something is changing per 1 unit. So if they give you the revenue function and they ask what's the rate of change or how is that revenue function changing from 2004 to 2006, go ahead and find the derivative of this thing. Our prime is the rate of change. Once you find the derivative, we're simply just going to evaluate that derivative at 6 years. Well, why at time 6? Because it says at time 4 corresponds to 2004, and we want to find at t equals 6 corresponding to 2006. So after you find the derivative, which is right here, you just, every time you see a t, you plug in a 6 and use your calculator to come up with the answer. I hope you find this video helpful. Here's a visual representation of that last word problem. If you have questions, feel free to email me.